So first we are going to talk about how to evaluate the mechanical property of material, and then we'll focus on the fundamental and critical definition of each mechanical property. Okay, let's get started. So the mechanical property of material is quite important because in order to properly design a machine and structure, we need to understand mechanical properties of material, right? So not this one. Yeah, design a machine and structure properly. And the mechanical property of material used in engineering design are determined by test of small specimen according various standard tests. So here you can see various standard tests, right? ASTM, ASA, JIS, something like that. Among them, ASTM is the most popular test method, and this is kind of real standard method all around the world. Okay, so many engineers follow the ASTM guide to take the and evaluate the mechanical properties of materials. And to obtain the stress-strain diagram of materials, the most common test is tension test for metal, right? So stress-strain diagram is very important diagram to understand the mechanical property of certain material. So for metal, normally use the tensile test, and compression tests are most used for rock and concrete, something like that. Another material, rock or concrete, and this is kind of ceramics. Okay. Then how to properly perform the tensile test using the certain metal. So we have to follow the standard method, ASTM standards, right? So in ASTM, there is a guide how to fabricate, how to build the standard specimen to evaluate certain materials' mechanical property, right? So it is possible to check the standard method to prepare the standard specimen. Okay. So ASTM standard cylindrical specimen are used to perform tensile tests. So using this ASTM standard method, we can make this. We call this is kind of some dog bone standard method or something like that. So basically, when the specimen is mounted on the testing system, this is the actually not standard, but typical tensile test machine. So this is the MTS. MTS means the brand name of this tensile tester. But there are two major, this kind of some tensile test manufacturer company. One is MTS, another one is Instron. So again, when the specimen is mounted, so here you can see the mounted specimen on the testing system, this MTS, both the load, right, the loading condition, and the elongation between gauge lengths can be measured. So here, this GL means gauge length. So by measuring this gauge length, actually we can define how this material can be elongated, something like that. And again, this is tensile test, so the tensile loading condition which means the tension, right, can be applied through this MTS again, the tensile testing system. Okay, so actually we can perform two different tests using this kind of typical tensile test machine. One is static test and the other one is dynamic test. So using static test, we can apply very slow loading condition. And for the dynamic test, the load rate is very high. So again, two different tests can be performed by using this kind of typical tensile tester. Okay, then again, using this typical tensile test machine, we can obtain stress strain curve. So here you can see what kind of specific the mechanical property can be defined by using the typical tensile tester. So by using the ASTM standard specimen for tensile test, which means tension test, basically there are two different concepts about stress strain, the relation. One is nominal stress strain and the other one is true stress and strain. So this is the nominal stress and nominal strain, and this is the group of true stress and true strain. Then what is the difference between nominal stress, strain, and true stress and strain? Okay, so if the initial area of the specimen is used in the calculation, the stress is called the nominal stress. So we can define the nominal stress, sigma nominal is equal to what? P over A0. A0 is in this case the initial area, right? Initial area. Then how to determine the nominal strain? Epsilon nominal. Once the initial gauge length is used in the calculation, actually, I'd like to check that. The initial gauge length in here is 2.0, right? That means this is the undeformed, right? Undeformed, the initial gauge length. So again, once the initial gauge length is used in the calculation, then the nominal strain can be obtained. So initial nominal, by following the definition of the strain, we can define that delta over L0. And sometimes we call nominal stress is engineering stress and nominal stress is engineering strain. Then what about true stress and true strain? The true stress can be calculated by using the actual area of the bar at the cross-section, which may vary during test. Right? So sigma true, which means true stress, can be identified as P over A, right? So in this case, A, we can define this is actual area. Then what about epsilon true? The true strain at any value of the load by using the actual distance between the gauge marks, right? So we can define that epsilon true is equal to delta over L. So basically the true stress is larger than the nominal stress because the actual area in a tension test is always less than the initial area because the cross-section area decreased during the tensile test, right? So true stress normally bigger than the nominal stress. In tension, true strain is always smaller than nominal strain because the length is elongated during tensile test, right? So the load, by applying the load on the specimen, the length is elongated. So always the nominal strain is larger than true strain, right? So here, I'd like to highlight that the sigma true is larger than sigma nominal because actual area in a tension test is less than the initial area. Initial area. Okay, what about this? Epsilon nominal is always larger than epsilon true because the length is elongated during tensile test. Okay. Then now we are going to discuss each critical mechanical property, right? So by performing the tensile test with certain tensile tester, such as MTS or strong, right? We can obtain this kind of some typical stress and strain curve, sigma stress, and epsilon represent strain, right? This is typical stress strain curve. So tension or compression, basically we discuss with the stress strain generating by the tensile test, okay? So tension tests are performed on a specimen with the stress and strain being determined at various magnitude of loading. Then we can obtain this specific stress and strain curve. The stress is plotted against the strain to achieve a stress-strain diagram for, basically we consider mild steel, low carbon steel. So the first, very important, the mechanical property is proportional limit. So, the proportional limit, the ordinate of the point A here, right? Point A is known as the proportional limit. And the maximum stress then may be developed during a simple tension test, such that the stress is a linear function of strain. All right? So, between point O and point A, we can obtain linear curve. And using this linear curve, linear stress strain curve, we can define the elastic modulus. So, the ratio of the unit stress to the unit strain is the modulus of elasticity of the material in tension under linear region, right? This is here, you can find that linear region. I told you guys between the point O and point A, the point O is kind of the initial point, right? And point A is the proportional limit. So, in this linear region, we can identify elastic modulus. And the elastic modulus, I told you guys in previous lecture, normally we specify the elastic modulus as capital E. And sometimes we call this is what? Young's modulus. Okay? And next important property is yield stress. Yield stress. Okay? So, here, the yield stress. Then what is the yield stress? There is an increase in strain with no increase in stress. So, actually, I would like to zoom in this specific region here. Then I can highlight that linear region and proportional limit A. And there is a B. And there is no stress change upper B point B. And between A, B, the increasing rate of stress decreased, right? And once the stress point reaches to the point B, which is the yield point, then the stress is no longer changing. So the yield stress is here. There is an increase in strain with no increase in stress, right? That is the yield point, and we call that is the yield stress. All right, then next important thing is the yielding, which means the perfect plasticity. So this one, this region. So the yielding region, the material deforms without an increase in the applied load. So I told you guys, once the stress strain curve reaches to the point B, the stress is no longer increase, right? And the yield point is continued to the stress, the propagation, not propagation actually. The stress, actually there is still exists some the exact the stress, the identity, right? The stress between the point B and point C, but there is no change of stress. We call that is perfectly plasticity region, which means yielding region. Okay, and strain hardening is here. Strain hardening, if a ductile material can be stressed considerably beyond the yield point, right? Yield point, which means the point B, without failure, it is said to strain hardening, right? So the material can reach to the basically maximum stress point. Okay, and actually I already told you guys the difference between nominal stress strain and true stress strain, right? So this, the actual red line represent the nominal stress strain curve. And this dashed line of stress strain curve represent true stress and strain curve. So I'd like to highlight one more time the stress strain curve with using the initial area and length of the specimen we call that is a nominal stress strain, and the stress strain curve with using the actual area and length of the specimen we call that is the true stress and strain, right? So basically, in case of the true stress and strain curve, right? This true stress and true strain curve, no decrease of stress occur, right? Always the stress increase. And another important point is the necking. So we can identify that again between the point C and point D, which means that strain hardening. Again, if the yield point, which means beyond the yield point without failure, the stress strain curve reaches to the maximum value of stress. That is here, ultimate stress point, which means the point D, the maximum stress point in case of the nominal stress strain. And again, the necking always can be found through the nominal stress strain curve. So the reduction in area of the certain mild steel bar becomes clearly visible with increasing strain. So suddenly the cross-section area of the mild steel decreased after passing through the ultimate stress point D. Then eventually the stress dramatically decreased. So we call this region is necking region. And after reach to the certain point passing through the necking region, here the point E, the material finally is fractured at this specific point E. So we call this is fracture point E. All right. So using this specific concept, you can define each specific definition. So again, proportional limit, I already told you guys the basic definition. Modulus of elasticity, which means Young's modulus, and yield stress, ultimate stress, and perfectly plastic region. All right, just check those specific definitions: strain hardening, necking, fracture, true stress strain curve, nominal stress strain curve. All right, you can check the detail of each specific definition. Actually, I already explained it. Okay. Then let's move on to the ductile and brittle materials. So we can actually make some group for the metal material. One group is called the ductile material. Another group is the brittle material. Then, what is the ductile and what is the brittle material? So here you can find that the ductile material. Ductile material is one having a relatively large tensile strain up to the point of rupture. For example, the structural steel or aluminum. So here, metals such as structural steel that undergo large permanent strains, that is very important point, large permanent strains before failure are classified as ductile. So again, aluminum, copper, lead, molybdenum, nickel, brass, bronze, nylon, something like that. Basically, those kind of some typical metal, we call that is the ductile material, right? And the brittle material, it's kind of some contrary concept, right? So brittle material has a relatively small strain up to the point of rupture, which means there's no yielding and no necking, okay? So relatively low values of strain are classified as brittle. So here, concrete, stone, cast iron, and glass, ceramic, something like that. These are the typical materials of the brittle the material. Okay, so here you can see the two different type of stress and strain curve, and each stress strain curve represent those ductile material and brittle material. Then just guess what is the ductile material stress strain curve and what is the brittle materials stress strain curve. Just guess. Actually, I already gave you guys the hint. Again, I told you brittle material, there is no what? There is no yielding and no necking, right? So we can identify that this, the right figure represent the brittle materials stress strain curve, right? And this left one, right? This is ductile materials stress strain curve. So the key is that in brittle material we cannot identify yielding region or necking region. Okay, only the ductile. In case of ductile, we can see the yielding and necking, which means the typical stress strain curve form, right? Okay, then let's discuss more about the detail, the mechanical property. Okay, so when a material such as the aluminum does not have an obvious yield point, even though this aluminum is also the metal and ductile material, sometimes this kind of specific metal does not have an obvious yield point and yet undergoes large strains after the proportional limit is exceeded. So in this case, we have to properly define the yielding stress region, right? Then in this case, an arbitrarily yield stress may be determined by the offset method. That is the offset method. So here, this is we call offset point. So used to determine an arbitrary yield stress, we have to use offset point. Then how to define this offset point? So for example, a straight line is drawn on the stress strain diagram parallel to the initial linear part. So like that. From this initial point O to the this is, I would like to highlight it as a proportional limit. We already defined that, the proportional limit, right? And between this point O and point proportional limit, PL, the curve shows the linear relation, right? All right, so we can draw the stress strain diagram parallel to the this initial linear part of the curve, right? This is the parallelly. I would like to change the highlight this one, right? All right, this one. So we can draw this parallelly offset with reference to the linear part of the initial stress strain curve. And the gap between the original linear part, which means between point O and between point O and proportional limit, and the parallelly drawn with reference to the this initial original linear curve, we have to define the distance, right, between these two OPL, and I would like to highlight that this as O prime and A. So the gap between these two lines should be follow the 0.2%, 0.2%. So that is the offset rate. So the intersection of the offset line and the stress strain curve point A, that is the offset point A, defines the offset yield stress. So here this should be what? Sigma y star, and we call this is offset yield stress. All right. Okay, so it is possible to identify the elastic modulus through this arbitrarily linear region. Okay, this is arbitrarily linear region because we draw this curve with reference to the original linear curve, right? So we can also define the elastic modulus through this arbitrarily drawn the linear curve. Right? Okay, so basically the offset yield stress is slightly above the proportional limit, right? The proportional limit here, and the offset yield stress is here. So basically the stress, the magnitude of the offset yield stress is slightly higher than its proportional limit. Okay. All right. Okay, so, sorry about that. I forgot to write down one important concept here. So the intersection, I already write down here, but yeah, actually I mark this arrow, right, to highlight the offset yield stress. So again, the offset yield stress is very important concept to define the arbitrarily the yield stress for the kind of the aluminum, right? The material which does not have an obvious yield point, right? Okay, then let's move on to the next slide. So I'd like to highlight one more time the true stress and strain and nominal stress and strain. And actually, I already told you guys the basic meaning, right? The concept of the stress strain and nominal stress strain curve. In this slide, I'd like to explain the difference between true stress strain and nominal stress strain using simple math, right? Using certain the equation, right? So definition of true strain, according to the basic definition of strain, we can obtain this specific expression. D epsilon T is equal to dl over L. And in this case, we consider the true stress and true strain. So L is what? L should be actual, not initial. Actual length. Actual length. So from this simple the differentiation, we can extend it. Epsilon T is integration L0L dl over L. And we can rewrite this form as log L over L0, ln L over L0. And the definition of L over L0 in this case is equal to 1 plus epsilon. 1 plus epsilon. Therefore, we can identify that the specific relation between true strain and nominal strain. True strain and nominal strain. Using this one, epsilon T is equal to ln 1 plus epsilon n. And actually for very small strain condition, epsilon T is equal to epsilon n, which means nominal strain. In specific condition of very, very small strain. Right? And what about the relation between true stress and true strain? The definition of true stress, we can define it. So by definition of true stress, we can obtain this again, the specific equation. Sigma T is equal to what? P over A. And in this case, again, A is what? Actual area. And the actual area is not equal to what? Initial area. Okay? And we need to assume that under certain condition of the volume of the material is the same before and after loading. It is true in plastic lanes. Right? So using this assumption, we can write down this specific equation. V0 should be equal to V1 because the volume does not change it. So A0, L0, if we know the specific area and the length, we can identify the volume of a certain material, right? And it should be equal to AL. Okay, and we can rewrite this equation like L over L0 is equal to A0 over A, right? And the A0 over A is equal to 1 plus epsilon. And in this case, epsilon is the nominal strain. Okay, so back to the first equation. The first equation, sigma is equal to P over A. Back to this equation. We can rewrite the overall, the relation like this. Sigma T is equal to P over A and P over A0 because we know the relation between the initial length and initial the area and actual length and actual area, right? So 1 plus epsilon n. And this P over A0 is equal to sigma n, which means nominal stress, right? So we can define sigma T is equal to sigma n 1 plus epsilon n. And again, for very small strain, sigma T should be equal to sigma, which means true stress is equal to true strain. Right? So, using this specific relation between true stress strain and nominal stress strain, we can draw the original, the stress strain curve, and which means original means the nominal stress strain curve, and true stress and true strain curve. And I already told you guys the true stress and true strain, there is no decrease of stress occur. So that is the difference between normal stress strain curve and true stress strain curve. Okay, I'd like to stop here and we'll continue to discuss ductility, okay, in next lecture. Okay.